Okay, I'm recording now. Okay, so hello everyone. I will start with this presentation. Do you? Okay. Okay, so now you see. Okay, so hello. This is CS.167. Let me go over some overview material. So this class is about learning what cryptography does. Okay, what is encryption? What's the signature? Message authentication, zero knowledge proof. Maybe more sophisticated stuff. We'll see. It is already plenty sophisticated, by the way. And how to construct these things. Okay. Now, the most important thing from my point of view, I mean, my philosophy, and not only mine, but a lot of people who teach this subject as well, is that the most important thing to understand is the security properties that the cryptographic tools provide. So technically, what is the security properties that something provides? And also, where does the security property, perhaps there could be a better one, stronger one, and that these things that you have in your hand provides property A, but not property B. And you better understand this when you're using these tools. You better understand what exactly is the properties that the encryption, signature, authentication, and what have you really gives you, so that you use it correctly. So that, the only way you can, you should use is to understand what is the purpose of these things is, and also where it stops, which will prevent you from misusing, which is quite common. People misuse cryptographic tools and basically create all sorts of trouble this way. So the sort of bread and butter of cryptographic activities that this class will introduce you to is, okay, here is an algorithm proposal. Does it achieve security properties that you would like it to achieve? Or does it not? And this ability to reason about an algorithm, does it give you the security properties that you wish for? Or, if it doesn't, what security properties, if any, does it give? This is the essential activity that we'll be introducing in this class. It's and unlike other parts of computer science, where you have an algorithm and what you're concerned with is basically just one thing: is it correct? Two, is it correct? Does it solve the problem on all cases, right? Regardless of the, does it in general find a partition through the graph? No matter what graph you give him, he always finds a partition. Or does it always find the minimum path between two nodes, no matter what the graph is, right, etc. Or does it always find an element or does it always sort an array regardless of what the initial arrangement is? And then the second question: how fast, right? How fast in the worst case? How fast of an average? Maybe some. You have different notions there, but and these answers basically can also be even if you cannot reason about them, if you basically cannot find an argument that would convince you that it works always, and if you cannot find an argument for how fast does it run, well, you can code it and you can test it. And if it worked on 10,000 cases, then maybe it does work always. And if it has some time behavior on 10,000 cases, then maybe it has this time behavior always, right? The thing is, with cryptography, you cannot do it. Like, you cannot prove in any, I mean, you cannot convince yourself that there is no bug, that there is no attack in such form, in such ways. There is no, prototyping does not help. I'm not sure that there is any other area in computer science, and if there is, let me know. There might be. That has, I mean, this is the most important thing for us, right? Like, I mean, that you encrypt and then you decrypt. Okay, I can test that. And how fast the encryption? Well, I can test that. But is this encryption secure? I cannot really test that. So what do I do? Okay, so this we'll study this exact question. And basically, why do we care about studying this question? Is it secure, right? So some wise men and women, decided that it's secure, so let's just trust them, okay? And most of you, are not going to be cryptography researchers. Maybe, a few will be, I mean, hopefully a lot of you will be very intrigued by this and enthusiastic about this and kind of wanted to study more, learn more, and so forth. But okay, maybe most of you are not going to be researchers in this area, right? So who cares how this is proven, how new algorithms are argued, right? Because you will not be giving new algorithms and arguing their security. The reason is, first of all, I do want you to do that. I would love you to come and be so fascinated by this topic to continue and learn more and possibly become, a cryptography specialist and even a researcher. But besides that, the act of understanding whether the algorithm satisfies security property basically really reveals what is the strength of this security property and where does it stop? Why it achieves this level and not that one? The process of understanding what these levels really are is, is the process of going through and sort of seeing for yourself. How would you argue that it achieves this one? And how would you argue that it doesn't achieve that one? Well, that part is often easier. There is an attack. There is an explicit attack that shows that this level of security is just not achieved because there is an efficient attacker who attacks. Is the proof that is harder. And but it's a really unique activity in the computer science. So that's what cryptography looks like, and here's your chance to just come and learn it, right? So I think this is the way to appreciate what the stuff really does and why, and then as you do that, you also learn, okay, here is the cryptographic thing. This is why it's constructed this way. This is why it shouldn't be changed. Here, the following thing, even though it looks more efficient, it actually breaks security. These are all good things to have to learn to use crypto correctly and cautiously. And also, I believe that there's just beautiful algorithms here. So, like, it basically does stuff that is counterintuitive, contain information and yet make it hard to get out, be a proof that some key existed and participated in creating a signature, but this proof is verifiable but cannot be reproduced on any new message to sign new messages on behalf of the key who signed some messages before. Without knowledge of the key itself. So all of these are quite perplexing, and when you see the solution, you hopefully will be like, okay, this is nice. Okay, so that's that's the spiel. So, okay, you know me, if you want to pronounce my name correctly, then it's Stanisław Jarecki, and I'm from Poland. You know, when we come online, you can find me in this room. TA is Bruno Freitas. By the way, he should tell us how to pronounce his name correctly too. And office hours was set by Doodle Pool. This class, it's good to be, you know, to have some intuition about algorithms. It will very much look like discrete math. The bread and butter is stating stuff concisely, and this looks very much like discrete math, the language that we use, right? And probability is good, but it's not super sophisticated, the probability we'll do here. So, you know, it's much simpler than the kind of probability that is needed, statistics in, you know, say, to understand, say, learning algorithms. And if you remember modular arithmetics from actually discrete math or some other math class, that is very helpful. But the level that is taught here at ECI in ICS 6D is just right to enter. And this class will very much feel like a theory class because it's about algorithms, and it's like understanding why the algorithm has some security properties. Stating the security property is basically like, it's another property of some algorithms, namely attacker. It's the property that attacker cannot do something, or that whatever it does, there is a low probability that he succeeds. And all of it is basically like a discrete math and or algorithms. And I still, you know, call this class applied cryptography, although that is controversial whether it should be called that, because I believe that this is the only way to understand how to use cryptography, and how in real world cryptography is used, and why you know, some decisions were made, and what are the limits of the tools that we have, and how to use them, how not to use them. But the skills with which you need to be able to reason about this, these are kind of like analysis of algorithms skills. So that's what the class will look like. You will be asked to prove some stuff, and maybe you haven't done that for quite a bit. So there will be some exercises where I'll be like asking you, okay, the whole point is like write a proof. If you think it's secure, a reason why. But this is only part of the exercises. There are others, and in general, you know, this is the kind of stuff where if you see finally the solution, it will be sort of, you know, once you understood it, it's easy. But finding the solution is not that easy. So you should not expect to solve all problems, and that's okay. So it's not, you know, solving all problems. Of course, you know, it gives you A+, but don't expect to, you know, and don't try to like copy and cheat just because you cannot solve all problems, because it is just way worse than solving the problems you can. Okay. So this is the textbook. I sent it to you on email, Katz Lendl. It's a second edition. There is a third edition out there, but I will stick to the second edition for now. In particular, it's cheaper. And anyway, the delta, it's fine. It's not that important. And I thought, well, the number of homeworks, maybe 5 or something like this, and then a final. And there will be Piazza. You will submit homeworks, and we'll grade them online using this site called Gradescope that you're probably all familiar with. And I want, for fairness, you can have study groups and you can find partners to Piazza, for example, right? Because we are all remote. So you can, I will encourage people to, to sort of find study partners. But if you work with someone, you must credit them as your collaborator. If we see that your solution is the same as somebody else and there is no credit, well, that's cheating. And also, if you copied the solution from some place, you have to credit it. First of all, don't try to search for this, but it might happen that you will basically see in some notes, in some material, essentially a solution, okay, credited. If failure to do so is just a report to academic honesty office, right? If there's any doubts about this, or any of this what I'm telling you will surprise you, let me know. Because I mean, it's always like, I taught this many times and I taught other classes and I think I'm very clear, and yet people do it. And then they claim like somehow ignorance, and I don't understand why. So do ask me, email or whatever, post on Piazza. You can also put anonymous, if you have some questions on this. Okay, so we're recording, but if you want to ask questions, so at the end of the class we put some time so off recording so you can ask. But if you want to ask now, it's fine too. Up we go to the so let's take overview a little more about crypto, okay, to just get a hang of the subject matter. So this is the first chapter of Katz Lindell, but not everything, and also reading this, it's nice because he we are complementary, not really. I'm not copying what Katz and Lindell write. So crypto is everywhere. Secure communication, file encryption, agreement on keys, authentication of users. Basically, all the more remote, the more mobile we are, the more forms of cryptography to secure these exchanges we need, and there is more applications, as we go. One of the sort of amazing ones that just popped up, a few years ago is the blockchain world, which just took off, and basically even general public, when they think crypto, they think of the electronic currency and not cryptography, but that stuff is built on cryptographic algorithms, and changes in the cryptographic algorithms that run it will affect security, efficiency, and other properties of this scheme, of blockchains, of electronic currency in particular. So there's tons of active research and work on all sort of fantastic crypto that is motivated by these new applications, and that is just one area, and there's many others. In general, as electronic life becomes more and more dominant, right, security and privacy and maybe anonymity will also are required, right? Okay, and here is the sort of Crypto 101. You have a HTTP session, right? You're browsing the web. There is a server and a client, and there is the HTTP protocol, but it's HTTPS, so it's secure HTTP. What on earth is this, right? Like, so, it used to be in this lower corner of what was this browser by Microsoft? I forgot, Edge or something. But yeah, it would tell you the little lock that you have. Oh yeah, Internet Explorer. Thank you. That you have the secure connection. But what does this mean, right? So there is two things that it does. When you have a secure connection, it means everybody who is, has access to this line, which, by the way, part of it from your browser, from your laptop, could be wireless. Even a server in some odd circumstance might be wireless, and the other part might go through also the routers that you don't really control and you shouldn't really trust. But HTTPS assures that in spite of this, nobody here on this who has access to this wire can eavesdrop or tamper with your traffic. They can do, if there are a router here, then they can do denial of service attack, right? They can just stop the connection. But that's the worst they can do. They cannot do anything else. They cannot inject new messages which were not sent by you. Well, also they can replay messages. So it's HTTPS is it's HTTP going over a secure socket layer. So what is secure socket layer? It's a secure version of TLS, right? Like the transport layer sessions. Now there are two parts of the secure TLS. First of all, the two ends, the client and the server, have to establish a key somehow. They don't have pre-established keys. Your laptop doesn't have any keys that it shares with, Chase, Bank of America, UCI. You might have a VPN, I'm not sure. But, with all the services that you want to talk to, it doesn't have keys, pairwise keys. It has to establish them. So how is that happening? How is that, how does that happen? Well, actually, and not only it has to create the key, but it has to somehow verify that the key is not shared by any Joe Schmo. As a server, I want to make sure that I share the key with an owner of a bank account that the client authenticates and says, I'm a Stanisław Jarecki, right? But so there has to be creating a key, but there's an authenticated creation of this key. And likewise for the client, a client should ensure that he's talking to the right server. But in order to do this, we need public key cryptography. So actually, even though this happens first in TLS, in the SSL, we'll do the second in the class because it's just more sophisticated stuff. If you first understand, you need to understand how symmetric crypto works to get to public key cryptography and not vice versa. So now imagine that the key is already pre-shared. Then the second question is how to use it to encrypt and authenticate the messages, the HTTP messages that are sent over this connection. And that is what we'll actually do in the first part of the class. So this is where symmetric crypto what symmetric encryption accomplishes. One of the things that it accomplishes. The workhorse of cryptography is symmetric encryption. It's a pair of algorithms, E for encrypt, D for decrypt. The algorithm E takes two inputs. So it parses its inputs into a pair and treats the first element as the key and the second element as the message that is to be encrypted. And it outputs a ciphertext, which we can now see. Decryption algorithm also parses its inputs as pair. The first element of the pair is the key, the second is the ciphertext, and it reverses encryption and decrypts. So now, algorithms, it's very important. Algorithms are publicly known. So the E algorithm and D algorithm is publicly known and are part of some standards that everybody can scrutinize, re-implement if they want to. There is no security by obscurity. So we do not rely on algorithms being obscure, being unknown by the attacker. Security has to hold even though attacker knows the algorithm E and he knows the algorithm D. What they don't know, we assume, is the key. So you need to, the whole security of encryption is predicated on you pick the key truly at random. The key doesn't have weak entropy because then all the security guarantees go bust. And you somehow keep it, close to your chest, and the attacker cannot enter you and just steal the key. Of course, in practice, this is exactly what happens, right? Laptops are, computers are taken over by viruses and other forms of attack, and they walk away with whatever key material is stored there. Then security properties are busted, right? But until that moment, you can protect them. This, by the way, is called Kirchhoff principle, that algorithms are public. It's only keys and other secret information that, other temporary values that can be assumed private. Already, when you talk about such simple thing as encryption, okay, simple, and it's not really, but there is at least two things that you can ask. What about encryption that just uses the key once? How can I use the key correctly if I know I can use, I just need to encrypt a single message and then the key, I'll just erase it. Even that question is non-trivial. And we will ask it at first. Of course, in practice, in most cases, what you want to do is you want to keep the key, like in this HTTPS example, the key is created once between the client and the server, and then you can encrypt any number of HTTP packets until, they say close the connection, right? So TLS has an instruction, you can close the connection. And SSL is just like has the same interface as TLS because it's just a secure version of TLS. So it has the same commands. So that's more, and we will do. Of course, this is what we want, but we will do the second, right? Because already understanding this is not so clear, and you have to take it step by step. There is other stuff that is happening in crypto. So you have this authenticated, so you have this key agreement, right? That thanks to which the Alice client and server Bob can create the same key K. And in such a way that whatever attacker listens to this traffic, they cannot get the key K. But maybe you would also like to do an authentication, right? So that well, hold on a second. I think I have to ask the kids here to to quiet down, right? Because I'm afraid that you might not hear super well. Hold on. I'm recording a lecture, so guys, keep your voices down. Just maybe surrender the phone. Well, because this way you will focus on something now, better. Okay, sorry. Okay, sorry about that. So Alice not only wants to establish this key, but she wants to know that she's talking to Bob, and so does and vice versa for Bob. So how is this accomplished? And of course, so these two are sort of what we showed on this picture, the SSL example. Basically, these are the two things that are basically crypto cores, right? Like this is the core of what crypto provides. It's good to understand how that works, but that's not all. So, for example, can you get an anonymous service? So could you get, for example, access your files and access them in such a way that the server doesn't know who you were? So you think, well, how can they? No, I mean, he can see which files were read. Well, but maybe he keeps the files in such a form that he doesn't know whether the person who wrote the file is the same one who read. The files are re-randomized at every access, so that the server cannot tell whether it's the same file that is accessed, on day 1 and day 5, or 2 different ones. And you can say, well, okay, and then you have a proper authentication on top of it, but the authentication is obfuscated in some way. So the access is assured that you only can access the files that you wrote, but the server still doesn't know. This actually is possible. It's not particularly efficient currently to achieve all these properties all at once, but it is feasible. And a lot of things in crypto were just feasibility results at first, and then practical systems later, because the crypto was improved and people have new ideas which make it faster, better. Okay, but that thing was actually possible. In a more general way, so this was just storage, right? I stored something, and then I accessed it, and the server didn't know whether it was the same person. If we all store files, and then only one of us retrieves it, the server doesn't know which one it is. Okay, but this is just storage and retrieval. How about more general computation? So if you think of what the search engine provides, is think of this as it's a database, right? You have some search query on this database, and you send the search query, and the database computes it, at first level locally. It's not true. It's a huge distributed system, but okay. Let's just pretend that it's a single database and it just does the local computation. How about, is it possible to have an encryption that what you send to the server is an encrypted query, and they somehow send you encrypted results, and the encryption is under your key. So you send an encrypted query, this engine cannot decrypt, so he doesn't know what the query is. But the encryption algorithm has the property that he can basically run the search from encrypted query from encrypted inputs to encrypted outputs, right? Because if you think of the database algorithm as, okay, database is just like an internal part of the algorithm. The input is the query, and the output is the result of the search. Well, can you have an encryption such that you take encrypted input, encrypted query, run the algorithm somehow on from encrypted inputs to encrypted outputs, and send this to the user, right? This also crypto can do. Not general complicated database query algorithms. It cannot do super fast. But it can do it in principle, and for some type of queries, it can actually do them fast already. The zero knowledge proof is, something some of you might have heard of. Is this another kind of counterintuitive property? So Bob is the server, a verifier. He has, let's say, we'll just call this a public key. Okay, you might have heard that RSA crypto system is based on factoring problem. What is a factoring problem? The factoring problem is this. You pick two large primes, P and Q, large meaning, let's have 1,000 digits each. You have efficient algorithms for finding prime numbers. You pick a random number and then you test for primality. And because the pretesting is fast, and the prime numbers are dense, meaning if you pick a random number, with decent probability you get that number is a prime. So you eventually find primes, and you multiply them. That's an, of course, easy operation. So taking inputs two primes, everybody can multiply them and create this output. But the reverse operation is not known to have an efficient algorithm. So if I give you a product of two primes, if the both primes were 1,000 bits each, then the product has 2,000 bits. So I give you a 2,000-bit integer that is the product of two large primes. And there is no efficient algorithms, meaning polynomial in the length of the description, which is 2,000 bits in this case. The best algorithms are essentially exponential in that size. Well, they're exponential in like a root of that size, but it doesn't change the asymptote, the picture. At least at first approximation. So it is, if you have this product of two primes, you do not know how to find the pre-image of this multiplication function. That's called that's factoring. So perhaps we can have an authentication like this. People like Alice will be associated with public keys, which are a product of the two primes. The primes are the private key. So Alice will keep the two primes P and Q, and she will give the public key N to servers. And then when she initializes an account with the server, and then every time she wants to log on, this guy will give her an access if she proves that she holds in her hands these two primes. Because somebody who just sees this composite integer, by factoring assumption, it's basically impossible. It's impossible for a polynomial time algorithm to compute the primes. So it's safe to give this, and nobody will be able to find these primes unless they break the factoring assumption. By the way, with the quantum computer, you can. So now what's the zero knowledge proof? Is there an algorithm thanks to which Alice, holding the two P and Q pre-images of this multiplication function, can convince Bob that she holds them that she holds two integers that multiply give n, and these two integers are not trivial, like none of them is equal to either 1 or n, in such a way that she leaves no other information. In particular, she does not allow Bob to replicate this proof, to turn around and to keep on proving to others that he is Alice, because he learned P and Q. So she cannot just send him, she cannot just send him P and Q, right? That would be a simple proof he can verify, but that's not zero knowledge proof. It's actually full knowledge proof. You give him exactly everything you know. So now he can go around and do proofs. Can there be a proof that you have this pre-image and the proof is convincing, so a verifier cannot, will not accept unless the proof is true, but the verifier learns nothing from this proof except of the one bit, which is that it is true. She does have this pre-image. It's called zero knowledge proof. And it sounds like an impossible property to achieve. And yet, actually you can. And for some many public key crypto systems that we're going to show in the second part of the class, you will see that you can do this quite efficiently. And this whole area is incredibly useful for blockchain applications. You could, if you knew how to efficiently prove that you have all sorts of stuff related to committed transaction, that would be fantastic. You could facilitate more sophisticated electronic commerce and better security properties and privacy properties for these transactions. So there's a lot of what seemed like a theoretical tool decades ago is an enabling vehicle for a lot of computer systems. Here is something that from some point of view is basically like a solution to all cryptographic problems, like a Uber solution. By Uber, I don't mean the car company, but the old meaning of the word. In general, people have computing problems can be phrased like this. There are several participants, Alice and Bob, client and server, different participants of the blockchain, okay, who have some inputs, and then there is some desired behavior based on those inputs. And the desired behavior is an algorithm. If you have the same password as mine, we should create the same key. And if you don't, you should learn nothing about my password. You should just get some garbage that is independent of my key. It's a simple algorithm if you think of this that way. So think of an election algorithm. People have binary votes, like Democrat and Republican. And there is an election center that basically counts, and it's supposed to take a majority, and that's the winner, right? So it's a very simple algorithm. Another example of such an algorithm is an auction. People submit bids, so these are numerical values, and the algorithm takes the highest bidder and or the second highest. So there's the Viceroy auction, right? Different auction algorithms. In general, they have inputs, and there is some function that is a function of these inputs. And they want to, if they have some trusted authority, like an election, or a bidding house, or whoever, they can submit these inputs, and the authority computes this function on it and gives them the result, right? So this is exactly how elections are organized, at first approximation, right? We trust some entity to run the correct algorithm, and bidding also. The question is, if you and I have the same password, right? And if I wanted to, okay, I will trust some authority to decide whether we have the same password. So I will give them my password, you will give them your password. They will just tell us whether they are equal. And if they are equal, they will give us the same key. And if they're not equal, then they will give us random values. Well, I don't want to authenticate that way, right? Who is this trusted authority? So we agreed to run elections this way because we have no other. We have no other technological means to do so. No other sociological, whatever, right? Society is used to having certain mechanisms, but clearly in solving general computing problems by trusting somebody to take everyone's inputs and somehow not reveal them, not to run away and do all sort of havoc with them. That's the number one. And also, just when they compute, actually compute honestly. Don't stuff the ballot box, or don't just tiny bit overbid over the second bidder so that you win the bidding, right? Or in the password example, just okay, I was stupid enough to reveal my password to this entity, so it just goes and authenticates to all my bank accounts with this, right? Is it possible, in general, if you have some computation and some distributed computing problem, could you instead have replaced this trusted authority and just implement exact same thing but without it? Okay, so what does this mean? It means that these people will follow a cryptographic protocol. If you believed, in any of this stuff I was telling you before, that you basically can have essentially that I encrypt your stuff, and you can run an algorithm on encrypted inputs. Then just think of this as follows: somehow you have an encryption that allows evaluation of F on encrypted inputs, and at the end you have an encrypted value of this output, but then the key is distributed between them. So they all create a key to begin with in such a way that only presence of all of them can actually imply the key, and nobody can skew the key. And so the final thing is just decrypted by all of them. So with elections, we all know it's a complicated system, and cryptographers were trying to propose more secure electronic elections, and there's so many societal concerns, legal concerns, that is actually a very difficult problem to engage, right? Which is not to say that it will not happen one day, but so far attempts at creating fully strong cryptographics through fully electronic elections have essentially not been successful. But the electronic bidding, that's actually how Google implements bidding on ads. So it actually runs a multi-party computation to basically convince people that it is done in a fair way, that no single computer that participates in this multi-party computation can skew and outbid. And yes, it's for fairness, or for perception of fairness, right? They can show that because it's this type of algorithms that runs it, it will be very hard to cheat, and that's good for their business, because it creates a trusted platform that you know, companies feel safe just you know, bidding on ads and they don't, you know, they're not afraid that their you know, business strategy is going to be replicated by someone else, and so forth, or so on and so forth. This I'm not sure that I will get to this, but I hope so, because it's really beautiful stuff, and it really looks like you know, it's kind of amazing, I think, that something like this can be done. And algorithms for secure multi-party computation are actually not so complex they go by a different description of the function, and you know, they're efficient depending on so I will just cutting to the chase. For example, if the function is described as a Boolean circuit, so you take you present all the x's as bits, and the function is Boolean circuit over these bits, right? So we know that all computation, hardware equals software, up to some polynomial factor. So everything can be represented just as hardware. What is hardware? Well, these are Boolean circuits. So and, not, or, right, etc. And the Boolean circuits compute, and the size of the circuit is, well, you can think of this as like, you know, if you want to implement something in hardware, that's how big the implementation would be. Okay, so like AES, advanced encryption standard, the cipher that we nowadays use, has, if I remember, no, something on the order of 10,000 Boolean gates. Bidding, you know, it depends on the number of bidders, but it's not a complicated circuit, and definitely, you know, election is not a complicated circuit. Yes, like taking a majority is not a complicated circuit. It's a very small circuit, actually, and shallow. The multi-party computation would be, its efficiency is linear in the size of the circuit. So for every gate, I do something, some encryption that basically does this gate on from encrypted inputs to encrypted outputs. And it's a beautiful stuff how this is done. And if you think this is, it's not, you know, even if I have 10,000 gates like this, I basically have 10,000 encryptions. And actually, I can do them using standard encryption. They're not some very complex, newfangled encryption. Generic encryption would work. So computing multi-party computation, even of sophisticated circuits, is within reach of practicality, and it is done for you know, in highly secure applications, or in for example, some blockchain applications, and also authentication applications, and there are many, you know, and coming applications for this stuff, like the auction run by Google to determine who gets to display an ad. Okay, Okay, so I guess I have two more things. Cryptography is engineering and science. So you want to state what your goals are security-wise, and and you want to somehow propose an algorithm that will accomplish them, and you need to prove that the algorithm accomplishes your goals. So in other words, that under the constraints imposed by the security goal, every attack, if it breaks the stated goals, then it's either impossible flat, like somehow information theoretically, you can argue that guessing the key that has n bits takes, has only 2 to the minus n probability, 1 into 2 to the n. But very often we'll have something called reduction, which means that we'll say, okay, if an attacker exists, it can be converted into breaking some underlying assumption, like, for example, factoring. So therefore, if you believe that factoring is hard, then the attacker against this crypto system couldn't exist. Because, again, there is a reduction that if the attacker existed, would use them to solve the underlying problem efficiently. So a lot of crypto propositions are really not unconditional statements, like attack cannot exist. They're conditional statements. Attack cannot exist if factoring problem is hard, right? And crypto is fundamental for computer security, and really a beautiful tool that can create like beautiful things that find usage, and they will keep on finding, and there will be more. So understanding how this works, I think, is is useful. But there's some disclaimers. It's not a solution for all problems. It cannot prevent software bugs, right? Like, so I have the best crypto system, but if it's badly implemented, there is attacks and human error. And so it's reliable only if it's implemented properly, and it works in the conditions that are matching what the person who created this assumed. If you write down your key on a piece of paper, or you are somehow not careful, then I cannot protect you with the cryptography. And it's beautiful if you understand it, but it's also sort of dangerous to try to play with it too much, without deep thinking. If you want to run something in the real world, you better double check it, triple check it, and do not run ad hoc designs, because the world is strewn with broken ad hoc designs. Understand what tool you should need, what the tools provide, and learn how to use them properly. And if you want to discover and play with stuff, well, actually, this class is the first place where you should be able to do so. With that, I will stop. And if there is any questions, we should be, I went over a little bit. But if you have any questions, just shoot them. Okay. I'll see you next time. Watch out for the email with the links and, where I'll be asking for vote. Thank you. Bye-bye. Till next time.
Thank you.